Good afternoon, evening, or morning, everyone, and thank you all for joining us today. My name is Dr. Tim Abbott, and I'll be moderating the seminar today. I am a postdoctoral fellow at the University of Waterloo in Ontario, Canada, and am IACCE's Associate Director for Youth and Public Outreach in North America. I would also like to extend greetings on behalf of IACCE's President, Dr. Jongho Lee, and the entire executive team and staff. But before we begin the seminar today, I'd like to take a moment to talk a little bit about IACCE and to provide a little bit of background. IACCE was established to help promote the development of a circular, science-driven economy. A circular economy entails gradually decoupling economic activity from the consumption of finite resources and by designing waste out of the system. This process mimics nature, in which waste from one process is the feedstock for another in an endless, infinite loop. A circular economy is regenerative by design and reimagines the traditional extract, consume, and dispose economic model, and instead redefines growth by focusing on positive society-wide benefits. Now, IACCE was established to promote the development of advanced knowledge, technologies, and policies in partnership with industry, academia, and governments, and to provide a platform for the exchange of knowledge. And developing a circular economy will require multiple key and intertwined areas and industries ranging from energy to manufacturing to agriculture and many others upon which IACCE is focused. And we invite everyone in attendance to become IACCE members. Individual memberships are open to all. And we currently have members ranging from students to professors, engineers to government officials and business executives, all from a wide range of industries from over a dozen countries around the world. And being a member offers many benefits, including access to events, networking opportunities, and materials, and will continue to grow as IAC does as well. And please visit IACCE.org for more information or to sign up. And now I am delighted to introduce tonight's keynote speaker, Dr. Jongho Lee. Dr. Lee is a noted researcher and an assistant professor in the Department of Civil Engineering at the University of British Columbia in Vancouver, BC, Canada. Dr. Lee earned his PhD from the Massachusetts Institute of Technology, or MIT, and was a postdoctoral research at Yale University. Dr. Lee's work is primarily focused on solving a wide range of problems in the water and energy nexus using membrane-based technologies of both experimental work as well as modeling. So, on behalf of IACCE and IACCE's student chapters, we welcome Dr. Lee.
Yeah, thanks, Tim, for the kind introduction. So hello, everyone. So my name is Jongho Lee from UBC. So hopefully today's talk will be well aligned with the theme of this IACCE. So the title is Emerging Membrane Technologies for Resource Harvesting from Wastewater. So the all human activities in residential, commercial, and industrial areas so produces a huge volume of wastewater, and as we can see in this this picture, all the various wastewater stream sources are collected and sent it to a facility called wastewater treatment plants. And traditionally, the wastewater has been always regarded as pollutants. So the main purpose of the wastewater treatment plants has been always to destroy or remove these pollutants. However, as Tim hinted in his introduction, this paradigm has been rapidly shifted in the last decade or so. The wastewater is now increasingly viewed as resource rather than pollutants because it has many substances in it, so including the clean water, fuels, electricity, and chemicals and fertilizer. All of these compounds are inside this wastewater. And because of this reason, the United Nations in 2017 designated the wastewater as untapped resource. So, so these materials are great. These compounds are great resources, but though as we know, the wastewater is a complex mixture of all of these compounds, and therefore the separation technologies are essential to extract these individual resources out of this wastewater. So there are many separation technologies, but today I'm going to focus on the membrane-based separation technologies. and hopefully show some interesting examples how these membrane technologies can be applied for selective recovery of resources. So generally speaking, membranes are, and simply speaking, the membranes are a sheet of filter papers. And in conventional membrane technologies, they use mainly a size exclusion, which means that the small molecules can pass through the pores, but the larger molecules are blocked. And that's how the selective recovery can be made. Or in some other technologies, such as reverse osmosis, reverse osmosis uses the contrast of transport rate between the molecules. So these technologies work well, but when the target compounds, when the target molecule of our interest, if the size is not that much different from other unwanted species, these mechanisms may not work very well. And especially when the target compounds are volatile, such as the methane, ammonia, fatty acid, and so on, so-called vapor gap membranes are more suitable approaches. So vapor gap membranes are, simply speaking, it's porous, non-wetting membranes. So because of this non-wetting nature, when this membrane is immersed in liquid, it captures air bubble inside its pores. So it forms a vapor gap. So only compounds that can travel back and forth across this membrane is gas phases. So, and in this approach, we can change the property of the solution of feed or permeate, such as temperature, pH, solubility, or polarity, and so on, so that we can selectively extract the compounds from wastewater into our final products. So today, I'd like to show 3 examples of these vapor gap membranes, how we can utilize these membranes for the selective recovery from wastewater. So namely clean water, methane as a fuel, and the biochemical as well. So first, let me start with clean water recovery. So as we know, following the agriculture sector, the industry is the second largest consumer of fresh water, consuming about 20% of the global fresh water. But in North America, such as in Canada and US, the industry consumes almost the same amount of fresh water as the agriculture sector. As a result, a huge volume of wastewater is produced by industry. So the reclamation of the fresh water out of this wastewater can significantly reduce the burden of freshwater supply. However, the industrial wastewater is very complex and often has very high salinity. For example, especially in the oil and gas sector, such as shale gas produced water, has very high salinity, which can go up to almost 300,000 ppm, which is about 8 or 9 times higher, 8 or 9 times saltier than the ocean water. And also, the power plant industry also produces very highly saline wastewater. So currently, the state-of-the-art desalination technology that produces fresh water out of industrial wastewater is the reverse osmosis. And then, as you can see here, so this chart shows the x-axis here is the salinity limit, the salinity limit of each technology, salinity limit of the wastewater that each technology can treat, and the y-axis is specific energy, which means the energy you have to provide to produce a cubic meter of fresh water out of wastewater. The reverse osmosis is very mature technology, so it has very energy efficient. It is very energy efficient technology, but the salinity limit that it can treat is about 70,000 ppm, which is twice higher than seawater salinity. But of course, there are other technologies, other thermal-based technology that can be able to treat much high salinity wastewater. But as you can see here, the energy consumption is orders of magnitude higher than the reverse osmosis. So the question is whether there is any other technology that can bridge this gap. And the answer is yes. Then this membrane, there is a technology called membrane distillation, which is suitable for high salinity wastewater treatment. This membrane distillation, simply called MD, is a hybrid process that combines thermal distillation and the membrane process. So basically, in this approach, a vapor gap membrane, which is non-wetting property, is placed between hot feed wastewater and cold permeate freshwater. And because of the non-wetting property, the liquid water cannot penetrate into spore. Only gas species, namely the vapor, can pass through the membrane from either one side to the other side. Now, when the feed wastewater has higher temperature than the permeate side, then the evaporation from this feed side is higher than from the permeate side. And as a result, water vapor is moving from hot to cold side. And this is how the distillation is done. And because salt doesn't evaporate, only water vapor can go through this membrane. So this is essentially distillation process happening inside the membrane. So that's why this is called membrane distillation. And this approach has several advantages over conventional reverse osmosis technology. First, the water flux across this membrane is nearly insensitive to the feed water salinity. So this is very suitable for high salinity wastewater treatment. And as I said, because salt doesn't evaporate, in principle, you can reject the almost complete, you can achieve almost complete rejection of the salt by distillation. And more importantly, you don't have to increase the temperature of this wastewater too high. You don't have to elevate the temperature up to like boiling points. As long as the feed water temperature is higher than the cold side, the permeate side, water vapor is always moving from hot to cold side. So we can utilize some waste heat from power plant and so on. So these are good advantages over the conventional desalination technologies. But the critical bottleneck of this membrane distillation is the membrane pore wetting. Because wastewater is not just water and salt, but it has a lot of other stuff, including the oil, grease, alcohol, and surfactants, and so on. And currently, all commercial hydrophobic membranes are able to repel water very well. So it's very, very hydrophobic, but it's usually is not suitable for repelling other liquids such as oil and alcohol, and they're easily wetted by oil or alcohol and surfactant and so on. So when these things are present in the wastewater, and it can wet these membrane pores, and then all the dissolved compounds such as salt, oil, organic compounds, and so on, it will just go through these membrane pores, and essentially the separation will fail. So the solution to that is to making a membrane that is very, very wetting resilient. So long story short, we have to make a membrane that is not only hydrophobic but also omniphobic, which means which can repel not only water but also any other liquid. So long story short, we take the commercial membranes. We take the commercial membrane, and throughout the nanostructural modification as well as surface chemistry treatment, we were able to develop an omniphobic membrane. For example, when we used the commercial hydrophobic membrane, it was able to repel the water and some detergent, but the membrane surface was easily wetted by oil or other organic solvents. But when we tested our omniphobic membrane that we developed in the lab, we were able to repel all those testing liquids. So we tested this membrane for desalination of the highly saline wastewater. So basically so this is the schematic diagram of our experimental setup. It's very simple setup actually. So we placed a membrane here in this membrane module, and then in one side, we circulate the wastewater at a higher temperature, about 60 degrees C. And then on the other side, we circulate the cold temperature deionized water. And the desalination happens across this membrane, so the water vapor is moving from feed to the permeate side. So this is the brief result of this test. So we first tested a commercial membrane, and in this graph, this x-axis is the time of the operation, and the y-axis here is the water flux and the salt rejection. So the rejection. Ideally, we want to have stable water flux as well as 100% salt rejection if wetting doesn't happen. And then we sequentially added the detergent into this feed water to promote wetting. And then this is the surface tension of the liquid of the feed water. Surface tension of feed water. The lower the surface tension is, the feed water can wet the membrane. So when we first tested the commercial membrane, the moment we injected the detergent into the feed water, the water flux suddenly goes high and the salt rejection goes down to 0. So which means that the membrane was clearly wetted and the separation just failed. But when we applied our the membrane, the omniphobic membrane that we developed, we were able to see the stable water flux throughout the entire experiment, as well as 100% of salt rejection. So at the end of the day, we were able to desalinate this the murky wastewater into this clean permeate water. So that was the clean water recovery part. And then let me switch gear to the methane recovery as a potential fuel. So as we know, the methane is a very potent greenhouse gas, which has about 25 times more higher global warming potential than CO2. And currently about 5% of the methane comes out of the wastewater sector. So even though this is very potent greenhouse gas, actually, as we all know, the methane is a primary constituent of natural gas. So for example, in Sweden, more than 80% of natural gas vehicles are running on methane, coming from the wastewater sector or the food waste. So in general, the wastewater treatment can be categorized into either aerobic process or anaerobic process. In the anaerobic process, the dissolved organisms can be converted to methane, and then that produced methane exists as either in gas phase or in the liquid phase. In most anaerobic processes, the produced methane is recovered from this gas phase product called biogas. Exists as a liquid phase, and then it simply can be discharged. However, when the organic concentration in the wastewater is relatively low, such as in municipal wastewater, as well as when the temperature is lower, the produced methane, a significant fraction of the produced methane actually exists as in the liquid phase. In fact, 40 to 60% of methane can be lost in the liquid effluent for the low strength wastewater at lower temperature, such as in ambient temperature. So this is not only the loss of a potential fuel, but also its release to the ambient. It can pose a significant emission of the global warming gas house, or global warming house gas. And so that's where our motivation comes in. So we wanted to develop a technology that can effectively capture this potent greenhouse gas and use that as an energy source. So we recently proposed a process called the solvent-based membrane contactor, SMC, for dissolved methane recovery. So the operating principle is quite similar to the membrane distillation that I presented in the previous slides, but slightly different. So here, this vapor gas membrane is again placed between the methane-rich wastewater and an organic solvent that has very high methane solubility and low water solubility, as well as low vapor pressure. So now, this vapor gas membrane has to be omniphobic because it has to resist wetting by both solvents. So from the water as well as from this the organic solvent. So we actually use these in-house made omniphobic membranes for this research. And now, because of the high methane solubility of this draw solution, it pours the dissolved methane into the draw solution. And at the second stage of the extraction, we can just simply use the vacuum extraction to recover this dissolved methane from this draw solvent, and then get obtain the final product as a gas product. So that was the basic the principle and idea. And we tested this idea in a very simple test here. So again, here the x-axis is the time of the operation, and y-axis is the methane concentration in the feed solution for different temperatures at the three different temperatures at the 15, 25, and 35 degrees C. So as you can see here, the initial concentration of methane in the feed water is higher when the temperature is lower, because the gas solubility is higher when the temperature is reduced. So as time goes by, you can see that the methane concentration is going down in the feed solution, and the methane concentration in the draw solution is increasing, which clearly shows the methane is moving from feed to the draw solution, And what's interesting to see here is that even when the methane concentration in the draw solution is higher than the feed solution, methane still moves from feed to the draw solution. And this shows a great advantage of this using solubility-driven mechanism for dissolved methane recovery. So after that, we actually we tried a very dirty wastewater that is saturated with the methane. So actually, this work was done by collaboration with Dr. Hyung-Soo Lee at Waterloo, and we received the food wastewater, the anaerobically treated food wastewater by anaerobic MBR as a feed source. And then when we tested this feed water for our SCMC process, we were actually surprised to see that this methane recovery performance was almost the same as for the case where we use very clean deionized water saturated with methane. So we didn't see any difference between the clean feed water and very dirty food waste water. So at the end of this experiment, we found that when we took out the membrane, we still see the membrane was quite clean. And then we tested exactly the same wastewater and same membrane for a conventional membrane process called the VMC, vacuum membrane contactor for dissolved methane. And then we saw that very, very severe fouling happened. So from this experiment, we saw that there is an additional advantage of this SCMC process, which is the process is quite highly tolerant to the membrane fouling. So finally, we also performed some energy analysis. We were curious whether this SCMC process can actually produce net energy out of the wastewater treatment. And for this purpose, we compared two other conventional processes for dissolved methane. So actually, the heating will never be used for the methane recovery. But for the sake of the comparison, we compared with this heating-based methane recovery. Basically, in this case, we assume that you can elevate the temperature of the wastewater and then release the dissolved methane from the wastewater. And as you can imagine, the energy consumption will be huge because you have to heat up the huge volume of wastewater, and then you can only get a handful amount of energy out of that as you recover the dissolved methane. And we also compare the energy consumption for the conventional approach for the dissolved methane recovery called vacuum membrane contactor. And even in this case, the energy consumption is still higher than the energy recovery by acquiring dissolved methane. But in this SCMC process, we were able to see the energy consumption is much lower, and therefore we can get the net energy production from this recovery process. So we thought that this novel process has a high potential to produce net energy by combining some existing anaerobic processes. And finally, let me briefly also talk about the biochemical, the recovery from wastewater. So as I just showed, the anaerobic process can convert organic waste into methane through methanogenesis. And this is the most common process for the organic waste into resource transformation. However, if we apply a different microbiology, then we can actually produce even higher value chemicals. The specific example that I'm going to talk about today is medium chain fatty acid, simply called MCFA. And first of all, so what is MCFA? MCFA is a saturated straight chain fatty acid that has 6 to 12 carbons. And the most commonly found MCFAs in the bioreactor are caproic acid or caprylic acid. And this is called medium chain, as opposed to the short chain fatty acids such as acetic acid or propionic acid, which has less number of carbons on their molecules. What is interesting about the MCFA is that it's very versatile chemicals. This MCFA can be directly used as a fuel, but also can work as a feedstock for many, many things, such as biofuels, pharmaceuticals, cosmetics, food additives, and so on. And more importantly, the market value of this MCFA is about 5 to 10 times larger than the methane. So this is a highly profitable chemicals if we can effectively recover from wastewater. And then currently, the most successful approach for this MCFA recovery from wastewater is called protraction. This protraction is a kind of membrane technology that has 2 stages, extraction and stripping. And this process involves 3 different solvents, which is obviously wastewater, and 1 organic liquid, which has high solubility of this MCFA, and a draw solution, which is a base solution that has high pH. And then these 3 liquids are divided, separated by the hydrophobic membrane. And in this process, at first, the MCFAs are dissolved into this organic liquid, and then these MCFAs are pumped to the stripping stages, and then this MCFA contact the draw solution and deprotonate it, and then finally they got into these draw solutions. So there are 2 stages, extraction and stripping stages, and this process is quite successful. You can recover more than 90% of MCFA from wastewater, but the downside of this protraction process is very slow because, as you can imagine, it involves 2 stages. So the transport rate is quite slow, and also it's quite energy consuming because you have to keep circulating this viscous organic liquid round and round. So recently we proposed this idea of using the supported liquid membrane to facilitate the MCF recovery as well as reducing the energy consumption. So essentially this supported liquid membrane is condensing these 2 stages into a very thin membrane. So the MCFA dissolved in this feed wastewater is directly go through this, selectively dissolved into this, the organic liquid inside this membrane, and it goes through, it is finally dissolved in this draw solution. So this supported liquid membrane is basically the vapor gap membrane that is filled with a specific organic liquid inside its pore. So in this way, we can actually anticipate that the transport rate of MCFA can be drastically increased. And also we can minimize the energy consumption, we can actually eliminate the energy consumption that we have to provide for circulating the organic liquid in the protraction process. Okay, so to test out this idea, we used the mixture of different fatty acid, including short chain fatty acid, as well as this caproic and caprylic acid, the MCFAs, and some ethanol. So just long story short, so this is the time of the operation, and y-axis is the mass fraction of each fatty acid. So we can see that in the feed water, the MCFA concentration is rapidly going down, and then we were able to see almost 100% recovery recovery of MCFA from the feed water, as opposed to very slow transport of the short-chain fatty acid. And from this experiment, we found that this process was more than like order of magnitude faster than the conventional protraction process. So this demonstration is quite it shows quite promise for fast recovery of MCFA from wastewater compared to the conventional process. And also we changed the liquid property, the property of the organic liquid embedded in this membrane, and we added an extractant called topo, and we changed the concentration of this molecule inside this liquid organic liquid. So what we found was that when the topo concentration is high, so this topo is, by the way, is a complexating agent that can wrap this fatty acid, and therefore it facilitates the transport of fatty acid across the membrane. So when the topo concentration is higher, we saw that all of this MCFA as well as short-chain fatty acid transfer rate is higher. And when the topo concentration was lower, actually we saw that this short-chain fatty acid were almost completely excluded, and only MCFA can pass through this membrane. So this is a great demonstration that this membrane can actually achieve a very highly selective MCFA extraction from wastewater. So these are the three examples that I prepared to share today. But of course, wastewater has many other things, right? So other examples that I didn't have time to share was like ammonia as well as waste heat. The ammonia is a traditional source of the fertilizer, and also ammonia is recently regarded as a great hydrogen carrier for fuel cell vehicles, and of course, and as we know, the wastewater has lots of ammonia, and then actually can supplement up to 30% of global ammonia production. And also waste heat, industry produces a huge amount of waste heat, and actually about 50%, half of the energy consumption was rejected to the environment as a waste heat. So if you can collect that waste heat, that will be a great resource as well. So just as a conclusion, so we think that these vapor organic membranes have great potential for selective resource recovery from wastewater, and the use of these vapor organic membranes, or in general these membrane technologies, can transform wastewater treatment facilities from traditionally resource consuming process to resource producing asset. So that's what I have today, and I'd like to thank all my students and postdoc, Xuesong, Abhishek Hiroki, and Sifat, and also collaborators, including Dr. Hyung-Soo Lee, I think who will be moving to Korea quite soon, and also Energia, as well as Fibercast, and also I acknowledge all other funding sources. And thanks everyone, and then I'd like to I'll be happy to answer any questions.
Right. Thank you very much for that extremely good talk. All right. So if there's any questions, please just feel free to unmute yourself and just blurt it out or put it in the chat. I see a hand up on Peter. Go ahead.
Thank you very much for your presentation, Dr. Lee. And I'm currently working on chain elongation to generate medium chain fatty acids from food waste. So I'm very curious about the possibilities for extraction. My only concern I'm having, and I'm wondering if you have looked into, how does it work when you're dealing with a really concentrated, silty, organics-rich wastewater?
Quite concentrated and salty organic wastewater. So I think that yeah, so basically the mechanism of the separation is the MCFA is, as you know, probably know, I mean, MCFA has a relatively long chain of carbon, so which is hydrophobic, right? So the purpose of this liquid is that this organic liquid has a non-polar liquid, which can dissolve the MCFA through the hydrophobic interaction. So that's how you can selectively dissolve these hydrophobic molecules, as opposed to all other hydrophilic molecules such as short chain fatty acid. I mean, relatively, the hydrophilic molecules such as short chain fatty acid, as well as water and salt or the ethanol, can be rejected. So that's what we observed. But one critical downside would be if there is a molecule that is hydrophobic but unwanted, then that will be a challenge. That will be also dissolved into this organic liquid. So, but if the molecule is very, very large, very long chain carbon chains, then that will surely be dissolved into this organic liquid and transfer. But because of the size, because of the big molecular size, transport very, very slower. So from there, you can actually get a little bit of more, selectivity.
I guess I'm more concerned about hydrophobic particles, or particles with a hydrophobic surface, which are larger than the 100 micrometer size and might become adhered to the hydrophobic surface and clog pores, and also attract that the MCFAs out of the solution instead of them passing into through the membrane and into the draw phase.
Yeah, so that's a great question. So I just said, if there is a hydrophobic particles, then it can also stick to the membrane surface, right? So that's definitely one concern. And then one thing that I wanted to say is that, so this fouling, the fouling based on this hydrophobic interaction was actually not severe when there is no water transfer. Well, there was no water transfer across this membrane. So I didn't mention this in the methane recovery part, but the reason why we didn't see much fouling when we did methane recovery was because there was no water transfer. There was no water transfer across the membrane. So when there is water flow, across this membrane, that actually bring the foulants to the surface, to the membrane surface. That aggravates fouling a lot. And then what we found is that if there is no water flow such like that, then the fouling was much gentle, much less. So we haven't tested the real wastewater yet, but that's definitely one thing that we really want to try. And then I also didn't present this here as well, but we have our own process for the anti-fouling surface treatment process. So when the fouling really becomes an issue, then our backup is that we can place a porous the anti-fouling layer on top of this membrane. So that's one backup. I think you are muted. Yeah.
All right. I'm not sure if you had another question there, Peter, or if you were good.
No, thank you very much. That
Okay.
covers everything.
All right, thank you. All right, and then maybe one follow-up question, if I may, that's sort of related to it is: have you examined the permeate for MCFAs for various pharmaceuticals or CECs, contaminants of emerging concern like PFAS?
Actually, no. So this was the first research that we actually just started, and then this results hasn't been published yet. So the paper is under review, and this is just the first study.
Okay.
So we haven't tested any like a complex wastewater or a complex mixture yet, but certainly that will be really, really interesting and necessary component of the research.
Yeah, very, very interesting to see. All right, I think there was another hands up that I saw. Was there, if someone had another question, can you raise your hand again?
Okay.
Or just say it there. Go ahead. Or I see
Hi.
Vikas. Yes, go ahead.
Hi, hello everyone. Can you hear me?
Yep.
Thank you, Dr. Lee, for the wonderful presentation. I have some questions regarding your organic liquid. When you ask for like you are using different organic liquid, so like my first question is: are you using different organic liquid for gas recovery and for the liquid, and for the medium chain fatty acid recovery, or are the same? So like how much is the organic liquid play an important role in your SLM?
Yeah. So that's a wonderful question. Thanks. So for the methane recovery, we used dodecane. We used the dodecane as the draw solution. We select that dodecane because dodecane has the 20 times dodecane has a 20 times higher solubility for methane compared to water. So there are other solutions. There must be other solvents that has even higher the solubility of methane compared to water. But we just selected, from the easy. I wouldn't say we were lazy, but we reviewed some solvents, and then the dodecane was the first thing that popped up into our eyes. And then also dodecane, because it's non-polar solution. It doesn't acquire water. So it prevents water transfer across the membrane. And also another important thing is that dodecane has some solubility of carbon dioxide. Yeah. So I think dodecane has twice higher solubility toward carbon dioxide above the water. So definitely CO2 will go through this membrane and dissolve in the dodecane. But because of the contrast of the solubility between the methane and the carbon dioxide, the methane transfer was much faster. And that's why the selection of this draw solution is very important. Ideally you want to select the solvent that has very high methane solubility and lower solubility for carbon dioxide as well as water. We haven't explained too much as the list of the solutions.
Yeah, thank you so much for the answer. I'm just very curious to know like how your SLM, how you're going to put your like your liquid in your membrane. Is it like a small thin membrane, or it's like a complete system where you will you put your liquid in? So I'm just curious. Is it like a thin sheet of membrane, or it's like a complete setup?
Yeah. So
and also with the I will just complete my question. I don't want to keep asking you a question. Maybe you can answer it right away with when you answer the first question. So it says like I also am wondering if what is the effect of their microbial falling and maybe the biofilm formation onto the surface. Have you ever seen any effect of maybe microbial or biofilm formation onto your membrane? And also about your economics, how expensive it would be if you wanted to use it for a large scale application. Thank you. Sorry for lot of questions.
Yeah. So okay, I try to remember as many questions as possible. But the first of all, for the experimental setup, I have to be humble enough that I admit our membrane testing setup is very simple. So for the SLM, the supported liquid membrane testing setup is very simple. So which is basically we take the sheet of the membrane, and then squeeze this this membrane is sandwiched by these two reservoirs. And then we just have a stirrer, and then we have the water jacket going around to control the temperature. And that's it. And then we sequentially, from time to time, at the designated time points, we take the samples, then measure the contents of MCFA and the fatty acid, and that's the experimental setup. But this actually related to the one of your I think this is the last question, but so whatever we are testing, whatever that I'm showing in today's talk is this flat sheet of membrane, this flat sheet type membrane. But in industrial applications, no one use actually this flat sheet membrane. The people usually use the hollow fiber membranes, which is like tubular shape of membrane. Okay, so and some of, for example, the membrane distillation, the first part of my talk, it's quite easy to transform whatever we find in this research into this this hollow tube module, because in the market the hollow fiber module of hydrophobic membranes exist, but this SLM as well as these omniphobe membranes for the methane recovery, the hollow fiber configuration is not existing in the market. So that's the one of the bottleneck. Even if all of the research is successful, you have to make a membrane in this hollow fiber module rather than the flow sheet, the paper sheet configuration. So that's one bottleneck for going to the commercialization. And I think you also asked biofouling, right?
Yeah, I also asked about the bioinformation on your membrane. I'm sorry.
No, yeah, so the biofouling, we didn't do any biofouling study, but what I think is that from the methane recovery part, my second part of the talk, so I showed that the fouling was very minimal in this process, even when you use very, very dirty wastewater. So yeah. I think that there will be some tolerance, but eventually when the biofilm actually grows, then that will block the membrane surface. But at the same time, we also did some theoretical study or modeling study. So what will be the impact of fouling layers? Eventually, the fouling will happen. Okay, so we found that the fouling will be slow, but eventually fouling will happen, right? So then what will be the impact of this fouling layer? So we found that for the methane recovery, the foulant layer doesn't have much resistance of the transport of methane. So that was a good news, but we have never tried the biofouling study, so we actually don't know whether that will be really true.
Thank you, Dr. Lee. Yeah, that was really interesting, because why I asked this question, because when you are planning to use it on wastewater, there may be chances that there may be a biofouling or maybe microbial attachment onto the surface. So though the surface, as you said, it's hydrophobic, so I believe that it should not have any attachment, but it's very interesting to see if there would be something like that. Thank you so much, Dr. Lee, for the wonderful answers and wonderful talk.
Thanks, because yeah, maybe I can add to that as well. It's just So I don't know if you are familiar with the water treatment membranes, but when the membrane is operated under very low pressure, then fouling will happen, but the attachment is very weak. So in that case, the cleaning is very easy. But when the membrane is under the high pressure operation, such as reverse osmosis, then the fouling layer attachment is very strong. So it's hard to remove the fouling layer. And then all three parts of my talk that I presented none of this is under operating the high pressure condition. So they're all operated under like an ambient pressure. So I hope that the cleaning, even if fouling happens, cleaning would be not that difficult.
All right, thank you for the excellent question, Sir Vikas. Is there any other questions that we have?
I'm just supporting. Vikas has one more question, actually, is not answered, and I'm curious as well. Like membrane technology for applying to the wastewater in a pilot scale or industrial scale is really very promising, and there are a lot of improvements during the decade in the membrane technologies. And I see that very amazing and very promising for your research as well. In the feed side, we have wastewater or whatever the feed is. And the other side, normally we get the clean permeate, which is water expected. But here we are looking into resource recovery, as well as another aspect is draw solution is organic solvent. And because asked one thing very interesting, that in the industrial scale, when we use membrane technology itself in conventional is very challenging for economic concern, high energy consumption and investment. So now draw solution as an organic solvent, it will bring another like the cost to the application of membrane technology. So how do you look into this for the real application?
Oh yeah, that's a wonderful question. Thanks for the question. So so for the methane recovery, if you remember, I used the dodecane or similar organic liquid as a draw solution. This is now one-time use. So basically, this is keep circulating. So when it collects the methane, dissolved methane, and then it's circulated and then vacuumed out, and then this solvent is regenerated. So there is this initial amount of the organic liquid you have to provide, but once you are doing that, you just keep circulating, and then you don't have to provide additional amount of this organic liquid. And then one of the reasons why we selected dodecane is that the vapor pressure of this dodecane is very, very low. So even after we vacuum out this this dodecane saturated methane for 24 hours, we didn't see any like a loss of the drop of the this dodecane. So that we lose almost nothing by this vacuum extraction. So there is not much like a chemical cost concern in that sense. And if that makes sense, or I don't know if this is a good answer to you, but that's one answer that I can give. And for the SLM, for the MCFA recovery, so basically the draw solution is the base solution, and then you are actually bringing in the acid. So you actually lose some OH, the hydroxide ions. And then in order to extract this dissolved MCFA as a product, you actually need a downstream process as well. But what we are now trying to do is that we are using the electrochemical process to acquire MCFA as an oil phase, and then regenerate the base as well. So you could, again, this makes the circulation possible, so that you don't have to add additional the solvent or draw solutions. And if that makes sense too.
Yeah, thank you. Yeah, it makes sense. I was just looking into this process. It is really very good that if we selectively separate some of the compounds, and also Tim asked one question that whether we can expand this one for emerging contaminants and others. That would be really very promising, that if we can do the sequential separation through the membrane process, different compounds. And I have one more big question, which is
it's a quick, we're running a little short on time.
Okay, sure. For the complex process of or the complex composition of the wastewater, whenever we selectively separate these things by membrane technology, how do you think that as a whole separation of the complete composition from the wastewater would be possible using membrane? How do you apply that principle in the membrane separation?
Yeah, that's actually a very big question. Yeah, I don't know if I can answer, but then I think that first of all, we have to do some economic assessment whether what will you extract. You have to decide what to extract, right? So, for example, the MCFA, MCF production is actually MCF production excludes methane production, right? So you are basically cut this methanogenesis and then go to the chain elongation. So by producing MCFA, you are actually giving up the methane, right? So you have to first make a decision. So which final compounds you want to extract, and then you have to decide which microbiology you want to select. So I mean, I don't know whether there is a good platform to judge which is more profitable or non-profitable. So I think that's the first thing we have to do. And then once we finalize and once we decide what to extract, then I think that the membrane technologies, one of the advantages of membrane technologies is modular, right? It's a module system. So you can actually place the module in a different sequence as you wish. So in that sense, you can, I think that you can make a partial or complete recovery of the desired compounds. But I don't know the answer and the complete answer yet. Yeah.
Lots of opportunity for research, that's for sure.
Yeah, thank you.
Perfect. And I know, Jongho, you have to leave here right away. So I think probably we'll have to wrap up questions here. But I just have one last little slide that I'll just sort of share with everyone. Switch this over. All right. So yes, I just, again, would like to thank our speaker for an extremely interesting and useful talk. I'd also like to thank Isabella Lee, IACCE as social media director and web designer for the many, many hours of work that she spent behind the scenes getting the website and everything else ready for this particular event. I'd also like to remind and to invite everyone as well of our next event coming up 2 weeks from tonight, which is on March 28th at 7 p.m. Eastern, so a half hour later. Where Michael Dorrington from Ontario Genomics will be talking about engineering and biology, to solve many of these complex problems as well. So if you would like to get some more information on that, or if you haven't registered, please visit our website, ia2c.org/events. And I'll also remain online for a little bit longer here if there's any further discussions or questions about IACCE. But that will otherwise conclude our seminar this evening. So again, I'd like to thank our speaker one last time, for his a good talk this evening. Thank you again.
Thank you very much. Yeah, I hope to see you again.
That's perfect.
Bye, everyone.
Okay, thanks. All right.
Before I leave, I have one thing to ask you.
Sure. If it's related to IACCE, maybe,
Yeah.
or if it's on microplastics, such as
It's for IACCE.
Oh, sure. Yes, of course. Go ahead.
Yeah, I think your membership is open for anyone who is interested in this organization to join. So
that's correct.
I tried to fill the form, and then I think it needs permission from the web advisor or whatever. So can you please direct it to your web?
Okay. Yeah, actually, someone else had contacted us earlier today saying that there was a problem with the web form. So we'll take a look at that. If anyone has tried to register and didn't, just send it. You can send me an email directly, or the info at ia2ce.org. Will also come to us as well. But in the meantime, Isabella, and I will take a look at the web form and see what's happening with that. So my apologies for that.
Okay, no problem.
Okay. And any other questions or discussion at all? Okay.
Thanks, Tim.
All right. Well, otherwise, I think we'll wrap it up. Again, thank you everyone for coming, and I wish everyone a good evening or a good morning for those joining us from Korea. It's nice to see you. So thanks for coming, and hopefully we'll see everyone back in 2 weeks. All right. Take care, everyone. Okay. Good night.